Hello, welcome to a new unit on atoms and the properties of atoms because of atoms and things like that. So let's say we had a piece of paper and I began to tear it in half and then in half again and then in half again. Is there a point where I could keep tearing it smaller and smaller in which it was no longer paper anymore, or would it always be paper no matter how many times I divided it? So after physically tearing it with my fingers, what I'd have is a really small piece of paper. But if I were to zoom in with a good enough microscope, okay, probably a scanning electron tunneling microscope, you would actually see that there's bits of matter surrounded by lots of nothing. And these little bits of matter are called atoms, and they come in different flavors. They group together to form molecules, or they bond with each other to form molecules. So everything is made up of atoms. Everything except nothing, okay, is made up of atoms surrounded by nothing. Okay, an atom is very small. Okay, if I had a teeny little marble and I blew up that marble to the size of the entire Earth, the individual atoms that made up that marble, okay, would only be the size of marbles themselves. Okay, so the atoms that made up that teeny marble when blown up to ginormous would only be the size of teeny marbles themselves. In a single drop of water, there's about this many atoms. Okay, that's a big number. And again, the point that I'm trying to reinforce is that atoms are very small. Okay, which is that number is about as many as there are drops of water on the planet. So in all the oceans and all the rivers, as many drops of water is about how many atoms there are in a single drop of water. Okay, atoms are small, so there's a lot of them. Okay, atoms come in different flavors, as I like to call them, but the correct term is they come in as different elements. Okay, there are hydrogen flavored atoms. There are oxygen-flavored atoms, okay, and there are carbon-flavored atoms, among many others, okay. The menu for the flavors of the atoms is the periodic table, and each one of these boxes represents a different kind of atom, okay, and this is an old periodic table. They've quote-unquote discovered or created some more of these. I think, I don't know, I hate to guess how many they've gone up to, but probably at least to 114, 116 by now. And so there's different types. Okay, once you separate these into atoms, you no longer have a piece of paper, because these atoms can recombine and form many other different things. For example, I can take two hydrogen atoms and an oxygen atom and get water. Okay. I can combine two oxygen atoms and a carbon atom and get carbon dioxide, which is in the breath that you exhale. It's a byproduct of metabolizing food. Okay, and these atoms that are around you have been around, since the beginning of the Earth and before that even. So they just constantly get recycled. When you die, okay, unless you're buried in a perfectly sealed rust-proof container, eventually your atoms will be recycled, and parts of your atoms might become a worm or a bird or another person or a building, or who knows. So your atoms the same atoms get used over and over again. Okay. When you exhale, your breath will become different things. That carbon dioxide in your breath will be reincorporated into plants and trees, and those plants and trees will get eaten and become part of other living things. So part of you is probably a salamander right now, and part of the carbon dioxide you breathe might even be a great white shark somewhere. Who knows? Okay. So when we die, what happens to our atoms? Well, I already mentioned that. They just get recycled, and unless you're in a perfectly sealed box, your atoms just get reused. Okay. Now, basically, the point of that was that everything is made up of atoms, and atoms are very small, and atoms come in different flavors. But for the most part, we won't be talking about atoms themselves. We're going to be talking about some phenomena based on the fact that things are atoms. Okay. So there's three states of matter. You've seen this before: solid, liquid, and gases. And the state of matter indicates how free the atoms are to move around, okay, and how close the atoms are to each other. Okay? And no matter what, unless you're at absolute zero, the atoms are always moving. Okay. So in a solid, okay, the atoms are the closest. Okay, I could see an easy multiple choice question along these lines. In what state of matter are the atoms the closest? That's in a solid. Okay, and the atoms are vibrating in place. Okay, they're able to move around a little bit, but they're stuck in the same basic spot. Okay. In a liquid, the atoms are able to move around each other, but they're still stuck together. They're still clumped together. They're a little further apart. Okay, and they're able to move around, which is why a liquid can flow and pour and things like that, whereas a solid can't. A solid comes out as just a chunk. Okay, but a liquid can pour because the atoms are able to move around each other. In a gas, okay, the atoms are the furthest apart, okay, and they're not clumped together anymore. They're able to completely move around the container. They take up the space in which they're in. Okay, they're just bouncing around, bouncing off each other, bouncing off the walls, and that kind of thing. Okay, so farthest apart, bouncing around. Okay. Now, if I had a container of gas, okay, like this, what's in between the atoms? Okay, the answer is nothing. Okay, the gas, you know, if this was air, the air is the atoms, and what's in between the atoms is nothing. Okay, air has a lot of nothing in it, which is why you can squish it. Okay, and that leads us to the next thing to talk about. So when I squish on a gas, okay, I'm able to squish it quite a bit. I'm able to compress it. Okay, is the correct term to say. Okay, I'm able to compress it quite a bit, and when I'm doing that, I'm getting the atoms closer together. Now there's a lot of space in between those atoms, which is why I'm able to get them closer together. In a liquid, I can compress it maybe just a tiny bit. This is an exaggeration. I can compress it just a tiny bit, and in a solid, I can almost compress it none at all. Okay. So why are we able to compress a gas a lot more easily than a solid? Okay. Can you see why it would be a lot easier to push the syringe in on a gas than a solid? Okay. The atoms are tightly packed in a solid, so there's really no room for the atoms to get closer together. Okay. In a liquid, there's a little bit of room, but it's still pretty tightly spaced. Okay. All right, so this is kind of a little bit of a review of a lot of things that you've seen before. Hopefully we'll go in a little bit deeper than what you've seen. The next topic that I want to cover is density. Okay? And what does it mean that something is very dense? You might say that it's very heavy, okay? And that's only partially correct. Okay, that's could be correct, it could be wrong. Okay, density indicates how compact the matter is in an object. Okay, and by compact, I mean how densely packed together the matter in an atom or in an object is. Okay, mathematically, it is the ratio of the mass and volume of an object, or in other words, D equals M over V. Okay, so density equals mass divided by volume. It's the ratio of the mass of an object divided by its size. Okay, so density equals mass over volume. Okay, mass, which is measured in kilograms or grams. Okay, and what type of instrument would you use to measure the mass of an object? Okay, what kind of instrument in a lab would you use? Oh, maybe a triple beam balance, maybe a spring scale, maybe a digital balance or something along those lines. Okay, and the size or the volume of an object is how much space the object takes up. Okay, measured in liters, milliliters, centimeters cubed, or meters cubed, among other ones. There's plenty of other volume measurements. And what type of instrument would you use to measure the volume of an object? Okay. Well, if it was a regular object like a cube, you might use a ruler and a little bit of math to figure out how big something is. If it was a liquid or a small enough object, you might use a graduated cylinder. And and I'm sure there's some other methods. Okay. What is the density of a rock which is 5 kilograms and 2 meters cubed? Okay, so 5 kilograms is our mass. Okay, so if mass goes on top, divided by meters cubed tells me that that's our volume. Okay, so divided by 2.5 meters cubed gives me a density of 2 kilograms per meter cubed. Remember, divide the numbers, divide the units. What's the density of a liquid which is 5 kilograms and 10 meters cubed? Okay, well, 5 kilograms is our mass still, and the volume, okay, is 10 meters cubed. So when we divide that, we get 0.5 kilograms per meter cubed. Okay, why did the density have a much lower? Why did the liquid have a much lower density, even though it had the same mass as the rock? Okay, it had a much lower density because it had a bigger volume. Okay, it took up more space. The atoms were spread out more. It was less dense. It was less compact. Okay. All right. So if you have a regular shape like a rectangular prism type object, length times width times height, you can use a ruler and measure these, and you can calculate the volume. Okay. If you've got a cylinder, okay, you can use a ruler to measure the radius, okay, and then the height, and you use pi r squared, okay, pi r squared h, okay, and that will get you the volume of a cylinder. Both of these equations are really base times height. Length times width is your base times height. Pi r squared is the area of the circle, okay, which is the same circle that's on the bottom, which is your base. And that's base times height. So, just a side note. Now, if you had kind of a weird shape, like a crescent moon, we don't have an equation for that, but we can still figure out the volume of that object. Okay? All we have to do is dunk it in some water. And when we dunk it in some water, we notice that the water level rises. Okay? And the object displaces, meaning pushes it out of the way, a volume of water equal to its own volume. Okay? So whatever volume this went up is equal to the volume of my shape. Okay? So if I wanted to note the change in volume, what piece of glassware is very good for measuring volumes of liquids? Okay? It is a type of cylinder. I'll give you a hint. It's graduated. Do you have it by now? It's a graduated cylinder. Okay? So here what you do to do this is you put some water in a graduated cylinder. So here's my graduated cylinder, the blue is my water. And then you record the initial volume. Okay? Then you put your object in, okay, and you record the final volume. Okay? And what do I do with these two numbers? So my initial volume is 12.3, 12.4, maybe 12.5, but 12.4 is probably better. Okay, here it's just a little bit under 15, so I said 14.9. Okay, what do I do with these two numbers to figure out the volume of the object? I subtract them. Okay, and we get that the volume of my object is 2.6 milliliters. Okay, I could now use that to calculate the density of the object. Now, would I want to do this before or after weighing the object to figure out its mass? I'd probably want to figure out the mass first in case it absorbed any water. Okay, so just as a side note there. So 2.6 milliliters is how much the water went up. Now, we've got some 8th graders doing this, and they make some typical 8th grader mistakes. So what's wrong here? So I put some water in, I recorded the volume, I put my object in, I record the new volume. Okay, well obviously the problem here is that the object isn't totally covered by the liquid. So that's not good. So I know what I'll do. I'll make sure I have plenty of liquid. I'll fill it all the way to the top of the measurement, all the way to the top of the graduations. Okay? And then stick it in. Okay, how did I do here? No, I didn't do good here either. Okay, because now the reading goes above my marking, so I can't read it. Okay, I know. I'll put less water in, and now I'll do it. Now I've got it going on. Okay? Well, we got a problem here is the object is floating. It still isn't displacing a liquid amount of water equal to its own size. I know what I'll do. I'll stick my finger in it, okay? Stick my finger in it and push it underneath, and now I'll get a good measurement, right? No, because my finger is displacing water. What would you do? I don't know. If you had a really, really skinny stick, it wouldn't displace much water. It wouldn't affect your results very much, like a piece of wire or something like that. That might work. Okay. All right. Another thing you can do is you can fill up a container up until it's completely full. So if you add a drop of water, a drop will come out of this spout. Okay. So empty out your container. Okay. After that, then drop your object in. Okay. Water comes out, fills up the container, and now you could read how much water is in the container using a graduated cylinder or a beaker or something like that. A graduated cylinder would be much better. Those are meant for measuring volumes. Beakers are not really. Okay, beakers are the ones that kind of are this shape, the glassware that's kind of like this, like a cup without a handle. Okay, so now when we're dealing with density, very commonly we're going to deal with units of grams per cubic centimeter or grams per milliliter. Now, a centimeter cubed is the same thing as a milliliter. Okay, so if you've heard of cc's, that's a cubic centimeter or centimeter cubed. A milliliter is the same thing, and a mil is sometimes referred to. So what's different about these units than the ones we're normally used to working with? Well, we normally always deal with kilograms and meters, okay, not grams and centimeters. But when dealing with density, it's just pretty common, okay? So that's the ones we're going to use. Okay, we'll use some kilograms per meter cubed, but only in a specific case. Okay. Now, one thing to note, that if water has a density of 1 gram per centimeter cubed, that means that every centimeter cubed of water has a mass of 1 gram. Okay, it's 1 gram for each centimeter cubed. Okay, lead, on the other hand, is 11. Okay, and air is a tiny fraction of that. Okay, if I asked you a question like, what would be the mass of 2 centimeters cubed of water? Well, you'd say each centimeter cubed has a mass of 1, and I've got 2 centimeters cubed, so I'd have a mass of 2 grams. Okay. What about a centimeter or half a centimeter cube of lead? Well, each centimeter cubed is 11 grams. I've got half a centimeter cubed, so it'd be 5.5 grams. Okay. I'm pretty sure this is a test question along these lines. So let's say I take one of those loaves of white bread, you know, the kind that you can mush into a ball and throw it like a snowball. Okay. So let's say I take one of those loaves of bread and I squish it. Okay, I wad it up into a ball. Okay, and the question is, what happens to the mass of the white bread when I squish it into a ball? Okay, assuming I didn't drop any crumbs. Well, the mass would stay the same. Okay. What would happen to the volume if I squish my my bread? My volume is going to decrease because it got smaller. What happens to the density of the bread if I squish the bread into a smaller volume? Well, think about what our definition of density means. It's how compact the matter is. Well, we made our bread more compact. We made the atoms closer together in a sense. Okay, it's kind of there's a little bit of some other things going on, but for the most part, let's just assume we made the atoms get closer together. And so what happens to the density? Well, the density increases. Okay, so the more compact the matter is, the more the density goes up. Okay. What happens to the mass, the volume, and density of water as I boil it into a gas? Okay. So here's my atoms of liquid water. Okay, and then I boil them, and they take up the whole container. Okay, so what happened to this was a sealed container, it was a closed container. Okay, what happened to the mass of the water? Okay, well, The mass didn't change. I didn't lose any atoms. I didn't gain any atoms. What happened to the volume of the water? Well, it was only this volume down here, and now it's the whole volume of the container. So it gained volume. Okay. So what happened to my density? If mass stays the same and volume goes up, mathematically my density goes down. Or you can think about it as what happened to the compactness of my atoms. Okay. Here they were more compact. Now they're less compact. So my density decreased. Okay. Which state of matter tends to be the most dense? That's probably a multiple choice question I might ask. Okay. Well, that would be a solid. Okay, with a gas being the least dense and a liquid being in between. Okay. What happens to the mass, volume, and density of water if I pour it out? Okay, let's say I've got 50 cubic centimeters of water, okay, and I pour down to 25 cubic centimeters of water. Okay, what happened to my mass? Well, I got rid of half my water, so I got half the mass. Okay, what happened to my volume? Well, it went from 50 down to 25, so I've got half the volume. Okay, what happened to my density of water? Well, mathematically, we can say we have the top, we have the bottom. The ratio will not change. Okay. The other thing we can say is that we didn't change how compact the atoms were. Okay, water molecules are still doing water molecule things. They're still the same separation. Okay, so I didn't change the density of water by pouring half of it out. Okay, so kind of this is important. Density only depends on what the substance is. It doesn't depend on how much of it you have because it's the ratio. Okay, so this is useful because we can use it to figure out what a substance is made of, because it doesn't depend on if I have a large chunk of lead or a little chunk of lead. The ratio is still 11 grams per centimeter cubed. Okay, so let's find the density of two materials. So 68 grams to 6.2 centimeters cubed, that's equal to 11. Okay, and let's say I've got 330 grams of another substance and its volume is 330 centimeters cubed. I get a density of 1. Okay. So first question is, does the substance with the greater mass always have more density? Okay, and this is an example of when it does not. This has greater mass. Okay, the reason it doesn't have a bigger density is because it also has a much larger volume. So when we divide by that much larger volume, we get less density. Okay, so now I can use a table of substances to identify what a substance is made of. For example, I could say that we know that water is a density of 1, so B is probably made of water, assuming it looks like water and has similar properties to water and similar other properties. Okay, and substance A, okay, is probably lead. Okay, assuming it has its other properties are consistent with lead. Okay. Okay. So density can be used to be able to identify a substance. So some questions that I might ask you along these lines, probably with different materials though. Which would have a greater mass? Okay, 1 cubic centimeter of water or 1 cubic centimeter of lead? So what we have is we've got the same size piece. Okay, which is going to have a bigger mass, the chunk of water or the chunk of lead? Okay, the chunk of lead is. Okay, it's going to have, water is going to have a mass of 1, and lead is going to have a mass of 11. Okay, so that's one way I can word this. The other way I can word this is this. Okay, which would have a greater volume? Okay, 1 gram of water or 1 gram of lead. So what I'm asking you is, to have the same amount of mass, which piece is going to take up more space? Okay. Well, lead is very, very dense, so I'm going to be able to get that mass in a very small piece. Okay, water is less dense. In order to have that mass, I'm going to need a full gram, or I'm going to need a full centimeter cubed. I'm going to need much less than that. of the lead. Okay, so the one with the greater volume in this case is going to be the water. Okay, so to have the same amount of mass, I'm going to need a bigger chunk of water than I am lead, because lead's more dense. Okay, so this is an example of a graduated cylinder type problem. A 73.4 gram block is dropped into a graduated cylinder, which initially reads 45.3 centimeters cubed. Okay, with the object in it, okay, it reads 64.1 cubic centimeters once it's dropped in, once the density of the block. Well, the first thing I need to do is figure out what the volume of the block is. Okay, that's how much the graduated cylinder level rose. So I'm going to take these two graduated cylinder readings and I'm going to subtract them and get that the volume is equal to 18.8 centimeters cubed. Okay. The next thing I'm going to do is use the density equals mass over volume equation. Okay, so the mass is 73.4. The volume is 18.8, which we just calculated. And we get that the density is equal to 3.9 grams per centimeter cubed. Now, what that would make that object made of, what would it be made out of, I don't know. But it's a good question. Okay, so work on the homework and good luck.